afternoon, folks, and welcome to another of our virtual tours of outer space. My name is Josh. I'm part of the Morrison Planetarium team at the California Academy of Sciences, and today we are delighted to be beaming from my house to yours, telling you about some of the really cool stuff going on in the universe around us, and a chance for us to do a very special kind of program, one that's normally very difficult to do in our planetarium. But this is one where I'm really responding to you. So if there's a place in our solar system or outside our solar system that you want to check out today, by all means, throw it at me. We are today going to be exploring in the OpenSpace software, which is exceptionally fun thing because it's something that you can actually download and play with at home. And at the urging of our engineers and our friends at OpenSpace, I have finally updated to 0.16, and we can explore a lot of things folks have been requesting that I have been previously unable to visit. So this is going to be a little bit of a learning curve for me, but we can be learning together. And I think that sounds awesome. So thank you for tuning in. I see some folks shouting out where they are from. I want to wholeheartedly encourage you. We are all tuning in probably from planet Earth, unless we have some folks on the International Space Station watching, but we are here checking out our own planet. Now, Earth looks exceptionally awesome in this software because, well, for a number of reasons. Number one, we have the most up-to-date photos of planet Earth. I always think this is really cool. When we look at a picture of Mars or a picture of Mercury, we are looking at photos that were taken a long time ago. For Mars, probably several years ago, and for Mercury, probably coming up on a decade ago. But when we look at Earth, we can see photos that were taken very recently. Like these, for example, you can see an awful lot of change in human habitation over the course of years. You can see fluctuations if you compare images over time, but specifically when you're seeing our clouds and weather pattern, we are seeing information from the Suomi spacecraft, and that's information that is just about a little under 24 hours old. I had to wind time back to actually February 9th GMT so that we would see an up-to-date photo of our planet today, but these are photos that are updated constantly. So you can actually track sort of the weather in your own area. I see a lot of folks tuning in from Canada, from Michigan, from Salinas, my hometown. We have folks from the Philippines tuning in. If you want to find out what the weather was like yesterday, I guess you could remember yesterday, or you could download OpenSpace and you can look for yourself, see those cloud patterns from above, which I always think is an exceptionally cool thing. So we can poke around on planet Earth, but we all grew up on planet Earth probably. So let's go see some other spots in our solar system, see if there's any place people would be interested in visiting, maybe a spot that you think would be really cool. I'm going to fulfill a request from several previous presentations where people asked me to show the asteroid belt. And first of all, I can give us a little bit of context by showing us about where the asteroid belt would be. And to do that, we are just going to take a big step back, zooming away. And as we do, you should be able to see some of the planetary trails. Let me see if I can get those in there. No, that's not working. Like I said, learning. But looking around here, you can see the sun, and let's bring in our asteroids. So the primary main belt of asteroids would be right around here. When people think asteroid belt, this is usually what comes to mind. Now, they're not yellow, they're dark mostly, very dark kind of grayish rock, little hints of red. But when we're talking about the asteroids, you can see they fall in this area relatively close to the sun. Now, recently, I think just a couple days ago, I saw an interesting paper put forward that was saying that we may have found a Trojan asteroid for Earth. And that's a tough sentence to decipher if you're not familiar with the terms. When we talk about the main belt of asteroids, these are ones that are orbiting the sun. They do so in what's called a torus, kind of a smushed donut shape. You can see that here. But we do see other families of asteroids traveling around the sun, some a little farther out. So I'm going to show you this group right here, just a bit farther from the sun. We heard about these from one of our experts not too long ago. These are the Jupiter Trojans. So you can always tell where Jupiter would be in relation to these. One of them is 60 degrees ahead Jupiter in its orbit. The other is 60 degrees behind. But they hang out and are influenced heavily by the motion of Jupiter. Well, we don't have big clouds of Trojan asteroids like this for Earth, or at least that's what we thought. This paper would suggest that we have actually found two objects that hang out in front of Earth in our orbit in a very similar way to they hang out around Jupiter. So I see Jared is suggesting the biggest asteroid is Ceres. I think that is a cool place to visit. I'm going to steal your idea, Jared, and take us over to Ceres. So Ceres, for those of you who are mythologies fans, is the goddess of harvest. Now, Demeter in Greek mythology, I believe, but Ceres is actually where we get the word cereal and is an exceptionally cool asteroid. When we zoom in, I like your quote, Katie. When we zoom in, we actually get a chance to see where Ceres is in relation to these other asteroids, kind of outside the main belt, but also away from the Trojans. Ceres is a little bit of a loner in that sense, all by itself. But it also brings home this really cool point. If we didn't have these giant yellow trails or green trails for our Trojans, you wouldn't really know those other objects are there. It turns out that when we're looking at things like this, we really don't see, let me see if I can turn on some, there we go, some texture on Ceres. And a little bit of topography, there we go. And this shows us something really cool. Notice how Ceres changed shape? If I go from here, it's perfectly round to not perfectly round. Round, not round. This is what we'd call an oblate spheroid, and it's actually representative of Ceres. It's not perfectly round. It is kind of lumpy and bumpy. We can see that it is a relatively round object because it is pretty big, but compared to worlds like Earth, it is still pretty lumpy, pretty bumpy. I forgot to turn off my asteroids, though. I'm not doing a very good job of cleaning up my workspace. So let me get in there and turn off my Trojans. Or else this is going to get to be a very confusing show very quickly. So in a program like this, we have the ability to show tons and tons of information. But if you don't turn off the information you're showing, things can get very confusing. So I wanted to take us out to see Ceres and some of the other really cool stuff going around our sun. We also have Vesta, is a really cool asteroid belt object, but I don't want to spend all of our time on the asteroid belt either. So if anyone here has a suggestion of someplace they would like to visit, I am all ears. In the meantime, though, I was talking about Jupiter, and now I want to go visit Jupiter. So let's set sail. This is going to be a relatively long trip if we were on a spacecraft, but we can do it in just a couple seconds. And our friends at OpenSpace told me about a super cool trick. If you hit Z, you go super speed, but don't hold Z too long because I routinely smash into objects now that I know that trick. And it is not fun for the audience to smash into objects. So looking at Jupiter, we can see this beautiful cloudy variation on the surface. I am a big fan of coffee, and I always think that the clouds of Jupiter look like when you pour cool cream into hot coffee, you get that beautiful swirling effect. And I think that looks a lot like the change in structure we see around here. I see some other suggestions popping up, though, so I don't want to stay on my picked object. Mary, where should we go next? Let's see. Pluto. We can absolutely do Pluto. So we are heading out to Pluto. Again, super speed, because if we were doing this from a spacecraft, you're talking about a decade from Earth to Pluto. Probably not quite as long from Jupiter to Pluto, depending on where they are in their orbits, or way longer, depending on where they are in their orbits. But I'm going to super speed us one more time so we can get to Pluto in a timely manner. Now, checking out Pluto, you can see a very gray surface. So I can also show you the simulated color version, which I think is kind of cool. Let's see if that pops in. Looking around here, I think one of the most awesome things is the variation on the surface. Now, I seem to have frozen slightly. Let's check that out. Okay. Huh. I seem to have very much frozen. We are going to keep talking in the off chance this is still sending out. There we go. I've gone over to the nighttime side. Let's see if we can get us back over to the daylit side. Okay. On the daylit side, you can see all that interesting change and variation on the surface. Someone's asking, Katie's asking, how accurate is the color? I would actually say if you want to see some really good shots of Pluto, we can see them. It should be a little bit pinker, kind of rosy, is a lot of the true color images I've seen. So looking around here, there is a lot of variation. on the surface in terms of texture. You will see some variation in terms of color, and I would point folks to other photos to really make sure that comes through. We should have this loaded up in OpenSpace 0.16. So if you tune in next week, maybe I can figure out what's going on and we can fix that up. But I don't know. This is still just amazing to me. I love looking at the variation, the craters on some parts, the absolutely slick surface in other spots. You can see that convection cells, the variation on the surface over here. This looks a little bit like a pot of boiling water, and there's a very good reason for that. What we are seeing is sort of boiling solid nitrogen. Now, it's probably about the consistency of toothpaste, so maybe solid isn't the right word, but warm stuff is mushing towards the top, cooler stuff is mushing down towards the bottom. Mary's just dropped some photos in there you can check out and see some really cool colors of Pluto. I believe those are saturation turned up a little bit, but you still get to see some really cool stuff. Ocean Misk is asking about Nibiru. Thankfully, just kidding. We're not going to go visit Nibiru because there's never been any observational evidence to suggest the existence of Nibiru. Nibiru, for some folks who might be interested, was sort of a conspiracy theory in the 70s. I think there were going to be aliens on Nibiru who were going to jump off Nibiru and come party with us on Earth. Parts of the idea sound super cool, and we have actually found some evidence to suggest there could be a 9th planet in our solar system. However, we just haven't found the planet yet. Turns out finding objects that far away from the sun is just a giant challenge. It's much farther out than Pluto, much, much farther out than Pluto, and probably not that bright an object. Do we have Makemake and Haumea? I believe we might have orbit lines for them, Anna. I don't know if we have actual models, but let's find out. No Haumea. No Makemake. Okay. So it's entirely possible that folks are able to make trajectories for those and plop them in, but as of right now, in the build that I am flying, I don't have those loaded up. I am pretty sure we got a Kuiper belt, though, Vishal, so let's put that in. We don't have a Kuiper belt. No. I can show you some of the stuff around Pluto, potentially, I guess. But for an actual Kuiper belt cloud, or Oort cloud, we might have an Oort cloud. Let's try that. Helps if you spell Oort cloud right. Okay, you ready? So this is a mathematical representation of the Oort cloud and how big it would be. I know what some of you are thinking. I thought the Oort cloud was made up of objects. Technically, the Oort cloud is a mathematical definition of a region that we thought objects would exist within. So I think the best way to show it is with a mathematical representation like a big geometric ball. So this sphere should encapsulate the area that we have our objects within. Micah is tuning in from OpenSpace to tell me to search for trans-Neptunian objects, not to search for the Kuiper belt. Okay, all labeling. Let's check out trans-Neptunian objects, not Trans-Siberian Railroad. There we go. So I'm going to turn that on, and this should give us kind of a cool way to show the difference in size, how far away the idea of the Oort cloud would be from the rest of the solar system. When we dive in, I'm going to keep that Oort cloud up. Check out these guys. So these are our Oort cloud, or excuse me, our Kuiper belt trans-Neptunians. These are things that cross the orbit of Neptune. So a lot of them would be part of the Kuiper belt, but they're not necessarily all part of the Kuiper belt. I would say these guys out here are more Kuiper belt-like, the ones at sort of the outside edge. But the other trans-Neptunians are on their inside paths where they're moving quicker, closer to the sun, and then they're going to shoot out past the orbit of Neptune. But anything that crosses the orbit of Neptune could fall within this category. So looking at this super cool structure here, these are things that are many light hours from the sun. Light would take, I think, 4 hours to hit the inner orbit of Neptune, and probably a little bit longer for these outer spots. Some of these objects travel very far from the inner part of the solar system. And when I say inner part of the solar system, I mean pretty much everything we think of as the solar system. But some of them could travel out here to the Oort cloud, but the Oort cloud is a reasonable representation of the farthest things that are still gravitationally bound to the sun, and that means it stretches out about 2 light years in every single direction from the sun. That's mind-boggling. So Katie wants to check out the name of the software. This is OpenSpace, and this is something you can check out too. When you're 2 light years away from the edge of the sun itself, imagine if I snap my fingers and the sun turned plaid, it would take 2 years for that information to get out to where you were. Anything that changes on the sun, you wouldn't know about it for 2 years after that event. That's how far away we are. And when we get farther and farther away, we're going deeper and deeper into interstellar space, the space between stars. And that to me is just wonderful and a little mind-boggling, but a really fun idea to hold on to. So I'm going to turn off our trans-Neptunian objects. I'm going to turn off our Oort cloud. Boop. And we are going to start heading back in. You can see some of our nearest stars over there. Neptune. Great idea, Kimberly. Let's go see Neptune. So Neptune, as we zoom in, we're coming from sort of very far away. I'm going to zoom us in. And let me know the first thing you notice about Neptune. Drop it in the comments there. I'm going to stay quiet for a second. It looks cool for sure. I think the color is really the thing that grabs me. It is so striking. You can see some variation in lightness versus darkness. There are equatorial bands and zones that kind of zoom around. We see light clouds and dark clouds, which I always think is super cool. There are storms, but this, to me, the color is just so striking. And that's a product of chemistry, photochemistry. We see a variety of compounds inside it. Like most of our planets, there's a component of hydrogen, probably a bit of helium, I would wager as well. We can also think about stuff like methanes. I believe there might be some ethane there too. It's a really big world. I think Jared was dropping some factoids in there for us. When we're talking about this, these are a category of world we call ice giants. Ice giants are bigger than our little terrestrials. Uranus and Neptune both fall in that category. And I don't know, it's just such a wonderful trip for me to imagine visiting a place like this, and you wouldn't really be able to walk on the surface, right? Because it's so stormy, number one. Number two, to even call something a surface implies sort of a rocky level like we have. Natalie wants to know, are the spots on Neptune storms? Many of them are. Some of them are cloudy regions. So if you see something that's got sort of that complex geometry, like an outer ring and an inner ring, I would say that's probably a storm. If you see sort of a smeary region of a single color, I would guess cloud. So this methane portion is really what we think is giving it this awesome change, this blue color that is so very striking. Now, I heard from a specialist that we don't really understand what's going on chemically inside Neptune, that there's a huge amount of unknowns into the nature of what's happening, the layer under where we see sunlight striking. Some sunlight must reach that, but we're not sure how much, because to understand how much sunlight would get there, we'd have to really understand what's happening to the sunlight in this outer layer. And for the layer under that, you'd have to really understand what's happening in the top 2 layers. And for the layer under that, you're going to have to understand what's happening in the top 3 layers. So when you put together all of these known unknowns, there's a really big head scratcher there. We don't know what's going on inside Neptune, and we really won't until we do a lot more studying and a lot more time spent on this amazing set of worlds, our ice giants. So we know there are ice giants around other stars. In fact, we're finding tons of ice giants around other stars. So that's telling us that we should be studying our ice giants a little better. Okay, let's see. Skylar and Jane want to check out Saturn. So let's go see Saturn. Saturn is again, beautiful, striking world. I think every planet in our solar system is wonderfully charismatic in its own special way. Saturn, for sure, is one of the most iconic and eye-catching. If you want to show something is cool and outer spacey, the easiest way to do it is to slap a ringed planet on it. So when you look at Saturn, those rings for sure jump out. You can see that wonderful shadow effect of the planet itself falling onto its rings, blocking some of the light that's striking them. It's easy to think that Saturn's rings glow because they are so bright, but in truth, they are just reflecting sunlight. They are a cloud of icy particles that are reflective. That's what gives them that brilliant color. Looking around here, you can see a little bit of the color variation on Saturn. It is sort of yellowy, maybe some dun. I mentioned bands and zones before and then did a very lazy thing by not defining what I meant. A band is a dark area, kind of a ring on the surface of Saturn. A zone would be a lighter area. But there's one very special, I would say, band up here at the North Pole of Saturn. And what is that? Well, that's the hexagon. We talk about the hexagon in some of our other programs. The hexagon is a stable storm-like structure on the North Pole of Saturn, and it really does look like a hexagon. There are great photos out there that are absolutely compelling, really fun to check out. And just to give you a sense of scale, I think, I'd want to double check this, but I think the hexagon is about 2.5 Earths wide. So that is a big structure. Now, zooming away from there, we can see... Oh, we can't see. My orbit lines are acting a little funny, but there's a ton of moons going around Saturn. When we talk about all these moons, we have just bajillions, not really bajillions, but I think there's 82 last time we checked. But Jupiter and Saturn are always in a race to see who has more moons. In truth, I would say we're never really going to know because there's a lot of tiny objects flying around these things. So looking around there, we can see that Saturn's a beautiful special object, but I see a ton of questions popping up. Janet wanted to know, how did the disk happen? We think that that actually used to be a moon. So I'm going to jump back to Saturn for just a second. You lured me back in. We think that a moon got a little too close and got shredded gravitationally, spread out and smeared all the way around the orbital plane for Saturn. So it's right around the equator, right above it. Michael's pointing out not bajillions, but certainly in the zillions. I think that's a reasonable estimation. And to Michael's point, or maybe as a counterpoint to Michael, I always want to know, what are we going to classify as a moon? When we asked an expert, the only definition she was willing to offer is if we can resolve it individually through a telescope. And that means if we point a telescope at Saturn, can we see it by itself? Or do we see it as part of a larger structure? Because in truth, like I said, those rings are made of teeny tiny particles, and they are orbiting Saturn. And there's not really a big difference between what we can see from Earth and a telescope and what's actually happening in the Saturnian system. So I would say as we get bigger and bigger telescopes, we're going to find more and more moons. And if we move our telescopes closer, we're going to find more and more moons. And one day, if we put a telescope in orbit around Saturn and we can individually resolve all those particles of the rings, I submit Saturn might have bajillions of moons because we're going to be able to resolve individually through a telescope all of those ringlet or particles. And that's going to be a very difficult day for kids who like memorizing the names of moons around planets. So, Titan. Thank you, Devin. Great idea. I love Titan. I am today naming Titan as my absolute favorite moon of the week because Titan is just so cool. When I say cool, I mean cool. It's supposed to be around 300 degrees below zero. When we look at Titan, its most awesome and grabbing feature, I think, is that super cool dark patches. Those dark patches we can see are actually liquid on the surface, or at least a lot of them are. There's also very dark sand on Titan. Now, that darkish sand is probably snowy particles, maybe condensates from the atmosphere, smushing around and sticking to some of the particles on the surface of Titan. But they do move around. They blow like sand dunes here on Earth, and that really, to me, evokes a really awesome scene. Imagine dark sand dunes and a dark ocean interacting with each other. I think that sounds super cool. And when you put the giant orange haze of Titan's atmosphere above it, it's like a Halloween beach party. You've got orange sky, black sand, and black ocean just sloshing around. It sounds absolutely wonderful. There's a lot of people who make visualizations, sort of a scientist's imagination of what it would look like to stand on a world like this. And it is just so fun to build out these ideas and come up with what it would be like to experience a world in a bit of a different way. And just to make it extra Halloween-y and spooky, a lot of the features on Titan, I believe, are named after sea monsters, which makes it extra cool. Maddie wants to see Enceladus next. I do believe I have Enceladus. Let's go visit Enceladus. That's another moon of Saturn. Ocean Mist pointed out that I'm naming favorites and maybe I shouldn't. Well, I love naming favorite moons. The problem is it changes pretty much every week. I get distracted by some article or something I've read about a new moon and I'm running off in a different direction. But I reserve the right to name whatever favorite I want. Looking at Enceladus, you can see, again, cool variation, but a pretty smooth surface. When we see something smooth, it often indicates there's not a lot of craters. Not having a lot of craters tells us that a surface is younger. When astronomers say something is younger, we mean less time since it's solidified. And looking down here onto Enceladus, you can see these cracks and surface features tell us about an active place. Now, some of these cracks we actually call the tiger stripes. They're close to the South Pole, and I'm going to see if I can't line us up well enough to see some. Ooh, does Enceladus have an atmosphere, Natalie? I would say no. It might have a couple particles, what some people like to call an exosphere, just little bits of gas trapped around it, but certainly not enough for me to call it an atmosphere, and nowhere near the kind of atmosphere we see on Titan, for example, or on planet Earth. So Enceladus, we have seen some of these particles flowing around it because it's got geysers that shoot material out into space. And for the moment, when a few particles are trapped around Enceladus, you might be able to say, well, technically, couldn't you call that? That's splitting hairs. I really don't think you should be calling that an atmosphere. Now, on Enceladus, one of the reasons it doesn't have an atmosphere is it is tiny, teeny tiny. Compared to Europa, which is another icy moon around Jupiter, which is about the size of our moon, Enceladus is almost nothing. It's a mini world. So you really want to see something fun. Think about how high you could jump on Earth and compare it to a much smaller world like Pluto. On Pluto, you could jump, I think it's 16 times higher than you could jump on planet Earth. If you visited a world like Enceladus and you had, I don't know, something to boost you a little bit, you'd be able to jump really high, maybe even escape velocity if you got going fast enough. Okay. What other solar system's body do we think are geologically active? Cool question, Michael. When we talk about geological activity, it defines a set of processes, stuff moving around on the insides. But I would say that a lot of the worlds we've seen, and I'm using that to include both planets and moons, have activity on the inside. We can talk about Enceladus. We could talk about Europa has activity, but they're fundamentally different processes than we see here on planet Earth. On planet Earth, we have radioactive decay going on deep inside our core that's sort of a battery. It's powering a lot of the activity on and in our planet. When we talk about Europa and Enceladus and even Io, another moon, I'm actually going to head out to Io because I think that sounds cool. We are talking about activity that is not necessarily coming from radioactive decay, so they're active but not active in the same way Earth is active. So calling them geologically active would be a kind of tough thing for me. But we do see that same internal activity, and that, I think, for some degree could imply that they are geologically active, even if it's a completely different process, one gravitationally powered instead of powered by radioactive decay. So I think the question was, what other solar system bodies? Starting from the top, Earth is for sure the most active. We see some volcanic activity on the surface of Venus, but no one's really sure how old it is. Mars was at one point volcanically active. It is no longer. We have Io, the world we're looking at orbiting Jupiter. We have Europa. We have some hints of activity on places like Pluto. We have hints of activity on places like Ceres. We're still not sure if those are currently active or were active in the past. But with Pluto, there is so much going on that it's hard for me to imagine that it's not got some activity up until the present date. So, depending on what you call geologically active, depending on what you call a world, there's a variety of answers you could have there. Michael specifically said solar system bodies. So, I don't know, if two asteroids bump into each other and water flows between them, does that count as geologically active? I don't know how to answer that question. Okay. Mary's suggesting, Angela wants to go see Mars. I think we can do that as a final stop real quick on our way back. Mary was asking another important question. When we say geo, we mean Earth. So would it be Io logically? Or there's a convention of using a Roman name for the sciences if we use a Greek name for the place. Or excuse me, switch that. Greek name for the sciences if we use a Roman name for the place. So Dan Tell, our engineer extraordinaire, has taken to calling the activity that would happen inside Mars as Areology, which would be the Ares of Greek mythology compared to the Roman name Mars for Mars itself. Oh boy. So flying around on Mars, you can see something kind of cool. We were talking about atmospheres before. If you check out the edge of Mars, you can see a little bit of a glow, kind of a yellowy haze. That is evidence of an atmosphere called atmospheric limning. We are seeing the kind of bubble of air wrapped around Mars. Not an atmosphere like we have on Earth, at least not nowhere near as dense, because we only see about 1% of the atmosphere on Mars that we enjoy here on planet Earth. And boy, do we enjoy it. If you dropped onto Mars, 1% of the atmosphere would almost be like being in a vacuum. Now, some science fiction movies certainly take liberties with what that would do to you, but it wouldn't be fun. So as we fly around on Mars, we are seeing some of the giant extinct volcanoes on the Tharsis Plain, and I wanted to get us over to Mars's perhaps hint that at one point it was going to be more geologically active than it is today. You can see over here the Valles Marineris, this gigantic canyon-like structure on the surface. This is what some scientists think was the start of plate activity. Basically, the same kind of tectonic plates we have here on Earth were beginning to form on Mars, but never quite got going. And this split that might have formed them became the biggest canyon structure human beings have ever seen. Now, that is something truly beautiful, truly special, and I really hope that scratched people's Mars itch. But with that, I would like to thank all of you for joining me here for our virtual tour of outer space. Thank you for all of the suggestions and cool ideas. We will continue to learn more and more about OpenSpace. There's some really fun stuff to see. I hope all of you get a chance to download it, enjoy it, play around with it yourself, and let me know what your favorite objects to visit are. Thank you for the OpenSpace team that tuned in to give us some helpful suggestions along the way. If you are excited about Mars, stay tuned. There's going to be some really big announcements this week, next week, about spacecraft arriving at Mars, even though in the past week we actually have had 2 successful missions reach Mars. But stay tuned, aerophiles. There's going to be some great stuff to see. So on behalf of myself, OpenSpace, the planetarium community as a whole who tuned in for the page, Mary, Morrison Planetarium, I think I already said OpenSpace, thank you for joining us here for our virtual tour of outer space, and have a wonderful rest of your day, wherever that day might find you.